Hi everybody, welcome back. In our last few videos, it seems like, the natural numbers and maybe the integers and in a few points the rational numbers have been sort of the star, right? We talked about countability and things like that, and we needed the natural numbers to be able to go through and make these post-it notes that we could use to count things, and they were kind of the star of the show. So in this video, we're going to finally see what the big deal is with the real numbers, why they're important. We know that they're not countable, there's a whole bunch of them. So what makes them so special, right? Why do we need all those decimal places and things? So to put things into perspective, let's go back and talk about the story of numbers. Right? If we were doing an algebra class, the truth is this screen here that we're about to go through would probably be most of what I would do in an algebra class, explaining all of the words I'm about to say in complete detail. For our purposes, we can imagine starting with the natural numbers, is, the way we count, right? One, two, three, four. I mean, little kids figure this out fairly quickly. When you say, I have one truck, I have two trucks, and so on. I have more trucks than you. I want that truck. Mine, mine. No, no. So well, positive integers are sort of a natural, normal part of life because we see those when we count, and we needed those when we talked about countability. Soon after that, though, we realized that we might go into debt and we might owe someone a truck or whatever. And so we may have a use for negative numbers and also zero. You have no truck. So the integers show up. Then, when things get slightly more sophisticated, we can make fractions. As long as we don't divide by zero, integer divided by integer, as long as the denominator is not zero, gives us a rational number. And so far, all three of those kinds of numbers are countable. So when we get to the real numbers, we saw that those aren't countable. There's just a whole bunch of them, which is really cool. But we will see finally this lecture sort of what they're good for. The complex numbers, I wish we had more time to spend on. Remember, those look like a real number plus I times a real number, where I, of course, is square root of minus 1. In my perspective as a complex analyst, that's where the real action is. But that's not what we're going to be doing in this lecture. So, to give you a hint of why we have all these different labels for these different kinds of numbers and why we make such a big deal out of each one, what is it that you can do with them? Well, with the natural numbers, the positive integers, we can add them, we can multiply them, and we still get positive integers back when we do that. So they're good for things like adding and multiplying. If that's the only algebra we needed to do, we could just use the positive integers. What we need the all of the integers for, throw in negative numbers and zero, is so that we can subtract, right? So that we have, if we were doing this in an algebra class, I would carefully say, so we have an additive inverse for everything. With the rational numbers, they show up so we can divide. Right? Or again, if I were doing algebra, I'd say, so we have a multiplicative inverse for everything except zero. The complex numbers are really cool because they're there so we can solve equations with quadratics, like x squared equals minus 1 is the most obvious one. Right? If you take two real numbers and multiply them together, you can never get a negative 1 because a positive times a positive is a positive, negative times a negative is a positive. There's no way you can make x squared ever be negative 1 if x is real. But you can with a complex number because x could be I. Okay? So that's really cool. And so the real numbers haven't gotten a lot of love lately. I mean, so what? What's special about them? Right? In a lot of ways, we don't really use all of the real numbers in parts of everyday life. For example, you don't often go to make a recipe and it call for I need pie, number of pie shells, right? You don't necessarily need all those decimal places. Even when you're doing a problem on a calculator, you usually cut off the decimal places after the first eight or so because the screen won't hold them. So, what's so special about R? Well, if we were doing algebra, then what I would spend like 3 or 4 weeks saying is that R is the completion of the quotient field of Z. That sounds really cool and complicated, and it is, and it's awesome. But since we're not doing algebra, I'm going to skip 2 hours of explaining what all that means and say what's special about R is this. We call this the completeness axiom. It means this is something we're just going to assume holds for R. We're not going to try to prove this. We're going to assume this is true. And this is what makes R different from the rational numbers or the integers or so forth. And this is that every non-empty subset that's bounded above has a least upper bound. Okay, so we need lots of definitions here. We need to talk about bounded and least and explaining what in the world that mess means. But this is what makes R special in a nutshell. Okay, so back to the definitions. What is this? What do those words mean? Well, suppose you have a set of real numbers. An upper bound for S would be a number, let's call it capital M, that's bigger than everything in S. So it's a number M so that for every X contained in the set S, capital M is bigger than or equal to that X. Okay? So if you have a set of real numbers, it's just, a number bigger than all of them. Okay? Now, the supremum of a set, which we would write as SUP, yes, like soup, is how we'll often say that. In fact, we'll say this a lot. So you're used to hearing the soup of a set. It doesn't have something to do with, a big pot with water and vegetables and things in it. It's not that kind of soup. The soup of a set is its least upper bound. Okay? The smallest number that would still be an upper bound. Okay, now, when you say definitions like it's the least upper bound, that's like the maximum of the minimum of the what. Say it's too much, right? So we'll need lots of examples, and we will do that briefly. So I want to give you the definitions first, and then we'll see several good examples. So if this is still a little confusing, um, after you've watched the examples, rewind this a couple of times so you can see the examples and the definitions next to each other. But in general, an upper bound is just a number bigger than everything else in the set, and the soup is the smallest one of those. Okay? If that upper bound is actually in the set, then we'll say it's its maximum. Now you're used to seeing maximums before, local max, local min in calculus, right? So something's a maximum if that's as big as it gets. That's exactly what happens. An upper bound is as big as it gets, and if that's actually an upper bound that's part of the set, so it actually does get that big, then we call it a maximum. Same thing works with lower bounds and same definitions. We just run all the inequalities the other way. So a lower bound is a number that's smaller than everything in the set, smaller or equal to. The nth is the biggest of all of these smallest numbers. And if the infimum is actually in the set, then we call it a minimum. Okay, definitely need an example. So let's look at a set. This is the set from -5 to 3. So this includes the -5 because of the bracket, doesn't include the 3. It's all the real numbers in between -5 and 3, counting the -5. It's bounded above. So we want to pause for a second and think, what are some numbers that are bigger than all the numbers in this set? Well, like 4 and 3.5, 26, pi. There's lots of numbers that are bigger than all the numbers in that set because all the numbers in this set live between -5, including the -5, and 3. So anything bigger than 3, right, is a upper bound. Well, what's its least upper bound? What's the smallest number that would still be an upper bound? Well, it's got to be 3, right? Because anything less than 3 won't be an upper bound. Like if you take 2.9, oh, well, there's 2.99999, which would be bigger than that. So anything less than 3 won't be an upper bound because the numbers go right up to 3. Anything more than 3, like 3.1, isn't least because 3.0001 would also still be an upper bound. So 3 is my upper bound. It's my least upper bound. So we'll call that the supremum. The soup of this set is 3. Okay? Does it have a maximum? Well, no, because 3 is not part of the set. Okay? So if there had been a bracket there that included the 3, then 3 would not just be the soup, it would be the maximum. Okay? Now, let's try this from the other direction. What are some lower bounds? Well, -6, -7, -2,524,000. Right? But the biggest upper bound, right, the one that gets closest there, would be -5. So -5 would be the nth, and -5 is also a minimum because it is actually part of the set. Okay, this helps, I think, too, to see this with a picture. I can't do this without. If you could see me in recording this lecture, I'm waving my hands all over the place and things because I really have to try to visualize this, and it does help to have a picture. So here's a picture. Here's an interval on the real line. You can imagine that it was, say, -5 to 3, like we had before. Then an upper bound would be some point where that green line is, something bigger than all the numbers in the set. Here would be another upper bound. You know, and there's another upper bound. I can keep sliding this down and finding more and more upper bounds. But eventually I slide it far enough that I can't slide it anymore. If I slid it any further, then it wouldn't be an upper bound anymore. That point where it stops, that's the soup of this set. That's what soup really means. And of course, inf is the same thing but on the other side. Now, your soup could be infinite if this set went all the way off to infinity. Your inf could be minus infinity if the set went all the way off to minus infinity and didn't have a lower bound at all. Okay? But showing this sort of picture, imagining a number line and what happens, I think is really helpful to keeping these ideas in your head. But okay, so what? Right? I mean, why does this matter? Right? I mean, I've showed you a picture of a line sliding around. Right? I mean, what's the big deal? What's special about R is supposed to be that every every set with an upper bound, right, has a least upper bound. Right? So can't we always just take that upper bound and just slide it down until we get the least one? Well, yeah, that's the point, right? Is we can just take that green upper bound that we saw in the picture a second ago, slide it down until it hits the the interval, and voila, right? Every set with an upper bound then would have a least upper bound. The completeness axiom says there aren't any holes where a number should be. Of course, that's a little concerning. Wait, what do you mean? Should we ever really been worried about holes? Well, think about this. You know, maybe there are the number line, right? Could have holes in it. It doesn't, right? But when you think about the rational numbers, if we just drew the rational numbers and not all the reals together, there would be gaps. It turns out that the rational numbers, you remember, are only countable, and the real numbers are much bigger. There's many more of them. So if we just put dots where the rational numbers are, there would be gaps between them, okay? And we wouldn't be able to do this wonderful trick of sliding the upper bound down until we hit the least upper bound, because the least upper bound might be a number that wasn't rational. It might be a place where there was a hole. This is why we don't use rational numbers for this. We need real numbers. Okay, so I think it would be worth proving to you at this point that there are some numbers that that are not rational, right? Because you may not have thought about it. I mean, most numbers you deal with are fractions, right? You may have run across numbers like pi before, and people said, "Oh, the you know the beat goes on, right? As decimal places go on forever and forever and forever." So there's numbers like that, but I mean, you don't. How much do you use pi in your everyday life with things? Um, it turns out that when the Greeks were figuring all this stuff out, they were absolutely floored that there were numbers you couldn't write as a fraction. And so there's lots of stories about this, about how Pythagoras and the Pythagoreans had figured this out, and that was one of their deep mathematical secrets. Um, and there's lots of stories about one of the initiates figured this out on his own, and they were either so disturbed by it that they wanted to get rid of it, or they didn't want the secret to get out. And either way, they killed him. So you can tell the story either way, and it's pretty cool. So here's our theorem: the square root of 2 is an irrational number. Now, how do I know that the square root of 2 is a number? And that makes sense. Well, I just talked about the Pythagoreans. The square root of 2 is the length of the hypotenuse of a right triangle where the base and the base and the height are both 1. Right? If you make a one leg and one leg that are each 1 unit long, which is not hard to do with sticks and a string, then the hypotenuse will have to be square root of 2. 1 squared plus 1 squared. You take the square root, you get square root of 2. So you can actually make something without too much difficulty whose length is square root of 2. And it turns out that the square root of 2 is an irrational number. You cannot write it as a fraction. It's not a member of Q. So that really disturbed the Pythagoreans. And it's a very, very cool theorem. We're going to go through the proof in lots of detail. But so knowing that there are numbers like that means if I tried to do that last example with Q and I had an interval that went from say -5 up to square root of 2, when I tried to slide my upper bound down, my least upper bound should hit at square root of 2. And square root of 2 is a real number, so that's fine for R. If I tried this for Q, there'd be a hole there where the square root of 2 should be. Okay, so how does the proof work? Well, I'm going to do this by assuming the square root of 2 is not irrational, which means I'm assuming the square root of 2 is rational. So that means I can write it as a fraction. And you can always write a fraction in lowest terms, so I'm going to assume that we do that. We cancel out anything in the top and the bottom, and so this is a reduced fraction. And so what kind of proof am I doing here? Well, obviously this is a proof by contradiction. I'm doing a contradiction proof because I'm assuming that I can write the square root of 2 as a reduced fraction. Okay, well, where from here? What can I do with that equation? Well, the whole thing about the square root of 2 is that when you square it, you get 2. So let's square both sides. That would tell me that 2 is equal to c squared over d squared. Okay. Well, it's kind of ugly because it's a fraction. Let's simplify this a little bit. Let's take the d squared to the other side. So that would give me that c squared is 2d squared. Okay. Okay, so what does that mean? Well, if you think back through some of the proofs we were writing earlier, it was exactly to set up this proof. Because all those homework problems where we talked about prove that this is even or this is odd or so forth, we did those partly because even and odd are easy ideas that you already know. And so it gives us something to work with when we write proofs. But also because I wanted to use it right here. So what this equation tells me is that c squared must be even. Because remember, the definition of a number being even is that it equals 2 times some positive integer, right? So, okay, great. How does that work? By the way, C and D both have to be positive. Of course, we can assume that because square root of 2 is positive. Right? It's a length. We know that. So this last equation says c squared must be even, or at least I could factor a 2 out. Another way of saying that. That means c has to be even. Now that's not obvious from the equation, but think about this. If c were odd, then we had a homework problem that said if you square an odd number, it has to be odd too, right? So c itself is even. So that means that I could write c as 2k for some integer k. Okay, so far so good. I mean, I've started out by assuming that I could write square root of 2 as a fraction. I squared it so I could simplify things a little bit. And I got that the c has to be even, use 2k. All right, so now what? Well, let's erase all this and get a clear screen here. So if c is equal to 2k, and I knew that 2d squared equals c squared because that was the original equation we started with, let's take that 2k and substitute in there for c. Okay. When we do that, we get 2k parentheses squared. And of course, if we square that, that becomes 4k squared. Okay, so what? Well, 2d squared equals 4k squared. That's just screaming out for somebody to cancel the 2's, right? So we could do that. We could divide through by 2. So it says d squared is 2k squared. Oh, wait a minute. That means that d squared is even, right? Because it's 2 times a positive integer. And the same logic we used a second ago. D has to be even, because if it were odd, when you squared it, you'd get an odd number. So that means that C and D are both even. But if C and D are both even, that's a contradiction, because we were claiming that we had gotten the C and D by writing square root of 2 as a fraction in lowest terms. We canceled off any common factors. And so the numerator and the denominator can't both be even because we assumed before we started we had canceled off any of the common terms. So square root of 2 can't be rational. Right? So again, this is sort of a big deal. It means that lots of effort goes into saying that the rationals were countable and the reals were not. So there was a lot more real numbers than there were rational numbers. And here's one of them. Square root of 2 is one of the real numbers, but isn't rational. Okay, what do you think about square root of 3? You think it's irrational? Well, that's a good question, right? It's worth going back through the proof and seeing what happens. Now, of course, we kept saying even and even and even over and over and over again because we were factoring out a 2, right? If we were dealing with square root of 3, you wouldn't want to factor out 2's and you wouldn't be saying things like even. You'd be saying divisible by 3. Right? What about square root of 4 or square root of 5? Well, of course, okay, square root of 4, that's rational because square root of 4 is 2, right? That's 2 is 2 over 1. Well, so it turns out that the square root of an integer, positive integer, is either another integer, like happens with square root of 4, or it's irrational, like with square root of 2. So the question is, how would you prove it? So you could use the same kind of argument, but instead of using even, right, we just need to use divisible. Right? So you'll get a chance to do that in the homework. Okay, so what's the point here? Well, the point is there's a lot of more real numbers than there are rational numbers, right? Lots of numbers are in R but not in Q. In fact, there has to be uncountably many numbers. The irrational numbers, the ones that are in R but not in Q, have to be uncountable because Q is countable and R isn't. So if you just put rational numbers on a number line, it would have a lot of holes where those irrational numbers, like square root of 2, should be. But R includes all those numbers, so there's no holes. That means that if we have a set with an upper bound, we can always slide that upper bound down until it hits the set and gives us a soup. Or if that number is actually part of the set, gives us a max. So what good was Q? Well, one very important fact about Q is that the rational numbers are all dense. That doesn't mean that they're not very smart or that they weigh a lot. What that's actually a technical term, and we'll see more about that word later. But one way of saying that in a way that we can understand for now is that between any two real numbers, there has to be a rational number and an irrational number. So rational numbers are sort of spread out everywhere. This is not too difficult to prove if you use real numbers as being things that have decimal places that go on. Well, if you give me two real numbers with their decimal expansions, then just get in between there and cut the decimal expansion off to get a rational number. And to get an irrational number, then just get in between there and then let the decimal expansion go on forever with no pattern.